All right, just wanted to announce that I got streaming already enabled because sometimes I forget, so it's kind of nice if people can remind me. But today I remember, so it's already on. All righty. Right. Well, it is time, so I'm going to get started first. I'm not sure how many of you have watched or read the announcement of IBM Z Day. So if you go to announcements, I just put this in today, and I wrote a little. It's not exactly an article. It is a just a description of what is IBM Z Day. So IBM used to be a lot more well known compared to where they are now. And that mostly has to do with these days. In addition to IBM, we also have other tech giants, including um, Google, Facebook, and so on. And back in the you know 80s or so, we don't have that many tech companies. Um, so the reason why I wanted to mention IBM Z Day, which is a day where they have conferences, that will be next Wednesday. So next Wednesday and next Tuesday are the 2 days where they have conferences. And the 14th is dedicated for students. So they want to invite students to understand what IBM is about, what their products are, and most importantly, from your perspective, the employment opportunities related to IBM mainframe computers. I think when I mention mainframe, most people would think really old clunky computers the size of a refrigerator, but the processing power of your fitness watch, right? Well, that's not actually true, okay? Because if you are talking about a hardware from the 60s, then yes, okay, that would be true. Okay, you are basically having a room full of computing equipment, and the combined processing power is about the same as your fitness watch. But these days, IBM still makes top of the line actual mainframe computers, and they are really fast, high performance, high reliability, and so on and so forth. Um, what is interesting about IBM is they maintain backward compatibility. So programs that was written in the 60s will still be able to run on a top of the line modern IBM mainframe computer. You would think that's a good thing, right? Complete backward compatibility. Well, it turns out it is sometimes a bad thing because now organizations that used to have these programs running from the 60s, they have very little incentive to renew their programs to run on modern platforms. So a lot of those programs, from the state, like the DMV and so on, they're still written in COBOL, COBOL, okay, COBOL. And COBOL is an interesting programming language. It is very verbose. You can read a COBOL program like a story, and no one can tell that. Is that a real program? Yeah, yeah, it's a real program. It sounds like a story because it's extremely verbose. Everything just sounds it sounds so good. But from the coding perspective, it is very limiting because that's before we have. Um, they don't even have recursion. You cannot have recursion in COBOL, not in the original COBOL, because they don't have a concept of a stack. There are a lot of things that they cannot do, but they excel at what it was invented to do, and that's why there are still programs, lots of programs used by huge corporations, still written in COBOL. But the original coders, the developers, they have already retired. Some have passed away. So these corporations and government branches were left with not enough people to maintain the code. And therefore, there's an opportunity for you guys, if you're interested in working with mainframe computers, there are plenty of opportunities now. So that's why I wanted to make sure that you guys are aware of this, at least to look into it. If this is not what you want to do, hey, not a problem. On the other hand, this is a great way to get employed by American Express, Wells Fargo Bank, even Raley's, our local supermarket chain. They use mainframe computers in the back end. Walmart, and if you want to join the state, there are lots of agencies who are really hurting to find people who can work with mainframe computers. All right, so that's my little pitch here. And with that done, we are moving back to talk about functions. So we are moving back to functions. Are there any questions about the assignment that was due today? The set theory thing. Do you want me to go over it? Okay, sure. All right, so let's go ahead and go over the set theory homework assignment. All right, so I'm just going to go through the questions one by one. Okay, the first question is, if A has the elements of AB and B has the elements of ABC, which of the following is true? Now this, with the bubbles, you can only choose one. Okay, it's not like a checkbox. So in this case, is A an element of B? Nope. Because none of these elements is a set. Okay, so that's the first clue that A cannot be an element of B. B is a subset of A. No, I think it's the other way around. A is a subset of B. Yeah, I think that is the case, but I need to check the last one just to make sure. The last one is B as an element of A. That would not be true. So the correct answer is the third one, which is A is a subset of B. Any questions? Discussions? Nope. Okay, moving on. Question number 2. So question number 2 is a little bit trickier because it has these check boxes, which means possibly more than one can be correct at the same time. So this one says, given that A union B has the elements of A, B, C, D, E, and then A minus B, or the difference between A and B, is only C and E, which of the following combinations of definitions of A and B satisfy this constraint? So the constraint is basically these two equalities here based on the union and also the differences between the sets. Select every combination that meets the constraint. All right, so this one is just going to be a little bit more tedious because you have to look at each one and see which one applies. This one does not apply. The first one cannot possibly apply even though it satisfies the requirement of the union. It does not satisfy the requirement of the difference, because what would be the difference between A and B for the first one? It will be an empty set, okay? It is a set that has nothing in it. So none is sort of the right answer, but not exactly. So it would not be part of the answer. The second one is A has CE and then B has A, B, C, D, E. Would that satisfy the constraints? No. It would not satisfy the constraints because when we look at A minus B, it would be the elements of A that cannot be found in B. B still has B and C and E, so this will not satisfy the second constraint, because with the second constraint applied to this particular combination, A minus B would have been an empty set as well, just like the first one. All right, the third one is A, B, C, D, E for set A and then A, B, D for set B. I think that meets the requirement, okay? Because C and E are missing in B, and yet the union of the two sets add up to the 5 elements that we need. This one does not satisfy the requirement because, once again, C and E are missing in A to begin with. There's no way it can meet that requirement. This one, we have ACE in A and then ABD in B. So we can see the CE are in A, but they are missing in B, so it does satisfy that requirement as well. With this one, it does not satisfy that requirement because A minus B in this case would have been A, B, C, D, E, all of them, because they're all missing in B because B is an empty set. With this one, it does not satisfy the requirement because we need C and E to be in A, but both of those are found in B, so it's not going to meet that requirement. Oh, by the way, what would be A minus B for the second to the last combination? ABD, right? So ABD would be A minus B in this case. And then the last one would also satisfy the requirement because when you look at the union, we get all 5 elements. But when you look at A minus B, it is indeed just C and E because B does not have CE either. Well, I shouldn't say either, but it does not have CE as elements. So it would be these 3 choices for question number 2. For question number 3, choose the correct answer. A is an element of a set where the only element is also a set that has A as an element in it. So you can see how the verbal, version of this notation is a little bit more tedious, and it can also be more confusing. The answer is false. That is not the case. Now, if I put curly braces between A, on the left-hand side of the element of, then the answer would have been true. Or if I remove the braces, surrounding A, so it only has one single level of braces, the answer would also be true. But in this form, the answer would be false. So anytime you guys want me to, kind of go into more explanation, just let me know, okay? Because otherwise I'm just gonna be working these questions out. And the answer is no. I actually do not actually remember, what questions I have put into the quiz. So I'm actually working all of these cases out as we, move along here. Question number 4, choose the correct answer. The set ABC is a subset of the set ABC. The answer is true because this is subset. It is not proper subset. So it does include a case when the 2 sets are actually the same. Question number 5. Choose the correct answer. ABC as a set union with AB is the set of ABC. The answer is true because each element can only appear up to once in a set. We do not say AA, BB, C as the union. Question number 6. What is the value of the following expression? So now this time you have to be careful because you have to look at the 3 possible choices. The first one says depends on how sets A and B are defined, which means in some cases it can be true, in other cases it can be false. The second one says false regardless of how A and B are defined. In other words, there's no way you can find a way to define A and B such that this implication is true. That's what the second choice is trying to say. The third choice is exactly the opposite. True regardless of how A and B are defined. Okay, so there's no way you can find a way to define A and B so that the implication turns out to be false. All right, so I cannot remember the correct answer to this one. We're going to have to work it out. So the way we work this out is to look at, the left-hand side of the implication, which is A minus B equals to the empty set. So if you remember, A minus B being an empty set means there is nothing in A that cannot be found in B. That's basically what it's saying. The other way to say the same thing is A is a subset of B. All right? So can I construct a case where A is not a subset of B? Oh, that's easy, right? They just have to contain different elements. Set A has XY, and then B has Z, okay? In that case, A would not be a subset of B. So that would automatically, cancel out this one. Because, if the left-hand side of an implication is false, then the implication itself is going to be true. So at least I can make the implication true. But is it always going to be true? Well, that kind of depends on the other side, which says A is not a proper subset of B. um, A is actually a proper subset of B. That would be pretty easy, right? You just start with A having the element of X, B having the elements of XY. So in that case, A is a proper subset of B. So this side is A is a proper subset of B is true, but the negation of that is going to be false. But at the same time, everything in A is also found in B, so that's why the A minus B is going to be the empty set. So this one, I can make the left-hand side true, the right-hand side false, and using the truth table of implication, the implication itself, which is the last operator of the entire expression, is going to be false. So it depends on how A and B are defined, so the proper answer is going to be the first one. It is not always going to be false. It's not going to be always going to be true. It depends. Question number 7, kind of the same deal, except the expressions are slightly different. So this time we have A union with B equals to A intersecting with B. The intersection of A and B is the same as the union of A and B, implies that A and B are the same. So intuitively, it is true, okay, which means that I should not be able to find a case where this is true, but this one is false. So I cannot come up with an actual proof right now, but that seems intuitive. Are we good so far? Okay. And for question number 8, which is our last question, what is the value of the following expression? A is an element of B implies that A is not a subset of B, okay, which is kind of the other way to say this, because this is properly if it's properly said, it is not the case that A is a subset of B, but it's easier for us to say A is not a subset of B. All right, so is it the case or not? Well, first of all, can we find a case where A is not an element of B? That's easy, right? Because all we have to do is to make A and B both the empty set. So if A is an empty set, B is an empty set, the empty set is an element of the empty set, has to be false. So that means the implication can be true, okay? So we have established that. So the next question is, can we make it false? Can we make the implication itself false? So that would involve A being an actual element of B, and A is also a subset of B. And in class, I think we have shown a few examples like that already. But in today's lecture, let me see if, I think Joplin is better for doing this, just because I can type a little bit faster than I can write, because I'm also prepared to write the answers. All right, so to make that happen, we have to make A an actual element of B. So we can make A the empty set, okay, which is easy to do. We can make B the set that contains the empty set as its only element. So this is how A and B are. Okay, so that's one requirement. And then the second one is we want A to be an actual subset of B to be true, because then this negation is going to be negating that would be false. So this is going to meet that requirement. Are we good so far with this? All right. So that's the okay. So let me answer this first, so I can submit and see if I'm actually right. I'm comparing what I think is right today versus what I thought was right a long time ago. Yes.
Is there a way to simplify this question?
To simplify this question?
Yeah, like I get really confused with implications.
But that's the whole purpose of the question, is to confuse you. So I can tell you how to work with the question like this, because the whole question is supposed to okay, so what do you mean by confusing you? Are you talking about the expression itself, or are you talking about how I phrase the possible answers?
The expression.
The expression itself? So one way to look at this expression is to look at it as a tree. Because what you want to do is to find out, okay, which operator works on what? Okay, what is on the left-hand side of what? So that's one thing you can do. And for this, let me see. Oh, okay, I got the right tool to do this. but I have to run the script first because otherwise the tool is not going to work. So let me do just that first. Okay. All right, I think it's this one. Fix. You guys cannot see it, but I'm fixing an issue with the stylus because otherwise it scales incorrectly and it won't work. But now that I have fixed that, I can now take a screenshot. So I think if I remember correctly, it's Shift Print Screen. So this allows me to capture a little part of the screen, and then I can put it into the quote unquote electronic whiteboard, which I am showing to you right now. That's the electronic whiteboard. And then I go back to the other side, paste it here, and I just need my stylus. And this is where it gets a little weird because I have to flatten my screen entirely, just so that I can write on it. So we're gonna do all this. So what you want to do is to basically say, the last operator is the implication. That's the last thing we apply. So now we want to determine what is on the left-hand side and what is on the right-hand side. So the left-hand side is just this. So that by itself is an operator, which is element of. And then the left-hand side of element of is the set A, and the right-hand side is the set B. On the other side, we have negation. Now, negation is one of the funny ones because it has one single operand. It's not a binary operator. It is a unary operator. So it doesn't branch out with two branches. Instead, it just says, okay, what am I negating? I am negating the result of subset of, and A is on the left-hand side, B is on the right-hand side. So this is a tree representation of the syntax. So now it is really clear what is the order of operation. Whatever A is an element of B is going to become, that becomes the left-hand side of the implication. A is a subset of B becomes the operand of negation, and then whatever the negation is giving us becomes the right-hand side of the implication. So is that going to help? Kind of, okay. This part is also getting recorded. This is the whole reason why I'm using a tablet, or a PC that has a stylus, so I can use it as if it is a tablet. Is I can avoid using the whiteboard entirely, so everything is going to be captured by YouTube. Are we doing okay so far? All right, so I got some confirmation. Okay, excellent. So getting back to here, I'm gonna submit my answer and see if I got 100%. And looks like, yep, so they're all green. So I'm getting 100%. Any questions about any one of these questions or its answer? No questions? We all good? All right. So now we're going to go back to functions. And today we're going to focus on properties that we can apply to functions. But before we do that, let me go back to show you guys where we are at this point. We are now at functions as sets, and we are supposed to be moving on to injection, surjection, and bijection. So probably the first thing we need to do is to get a quick review of what qualifies a set as a function. And all right, so let me just make sure that we can. Oh, by the way, are there any questions about the application of why we need to define functions like the way we do? Remember that homework assignment, from another professor, who wants me to write a sorting algorithm, and if the property of the output is not done correctly, I can cheat, right? I can just say, oh, I will just make everything 0, and it will meet the requirement of A bracket 0 is less than or equal to A bracket 1, which is less than or equal to A bracket 2, and so on. Because there's nothing in that description that says, oh, you have to start with the original values, or whatever was in the original array still has to be there. So I have to be very careful about how I express that. That's one reason why we are looking at functions. The second thing, the original thing that I wanted to say was, what makes a set a function? Okay, what are the qualifications? So one thing you have to first come up with is what is supposed to be the domain and what is supposed to be the codomain. Without knowing what is supposed to be the domain and the codomain, I cannot tell you whether a set is a function or not. Well, not in some cases. In certain cases, yes, I can, because every single element in a function is supposed to be what? I'll give you two choices, okay? Every element is in the function as a set is supposed to be a two tuple, or is it supposed to be something that's just a single value? It has to be a two tuple. So if you have a set where at least one thing in it is not a two tuple, then you know for sure that set cannot be a function. Okay, so that's pretty easy. In fact, we have to say that if you give me a proposed domain and a proposed codomain, the function as a set has to be a subset of the Cartesian product between the domain and the codomain. That's one simple, easy requirement. And are we okay in terms of what Cartesian product is? Do you guys all remember what is Cartesian product? Okay, all right, very good. So what about the second requirement? The second requirement is this thing here. So let me give you an example of what meets the first requirement, but it is far from meeting the second requirement. So in this case, I think Joplin is the better tool to do. All right, so I'm going to give you a notation here, which is F right arrow. Okay, no, that's not the right one. F colon X and then right arrow Y. So this is basically saying, I think we have a function F, and it's using X as a set of domain, and Y as a set of the codomain. That's the notation. So if we think that X is a domain and Y is a codomain, so we can now have an example like AB for X, and we'll have Y being 1, 2. Okay, so that's one thing. So now the question is a particular set really a function? So now we can say, okay, let's take a look at F having the following elements. So we have A1 and A2. That would not be a function. It is not a function because it broke the rule of every element in the domain has to map to one and only one thing in the codomain, but it broke the rule of every element in the domain. Because what's happening to B as an element of the supposedly domain is not mapped to anything. And it broke the other rule as well, which is every element has to map to one and only one. Element A is mapped to two elements in the codomain. So it broke two rules at the same time. Okay, give you another example. So if I have F, and this time I change it just slightly, so that we have A1 and B1. This one is a function. So even though some people may scream at me and say, but this one has the reverse problem because we have one element in the codomain, 2, that is not mapped to. Both elements in the domain map to the one single element of 1 in the codomain, leaving the element 2 not mapped to at all. Well, but that's okay, because did it meet all the requirements that I said earlier? First, every element in the domain is mapped to blah, 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 blah. One and only one element in the codomain. It met the requirement. It didn't say anything about uniqueness. So A and B do not need to map to different things in the codomain. So that's why, this is still meeting all the requirements. All right, so I just want to show you some examples. But more importantly, we look back into this expression here, which is quantified, because this is the quantifier, and then this is the actual predicate, or this is the actual expression that we want to be true for every single E in order for the entire quantified expression to be true. So this is it, okay? We need this whole thing to be true. And I explained this particular expression last time as well. So I hope you guys still remember how to read something like that, because we're going to see this again today in a slightly different form. Are we good so far? So this is just a review of what we have gone through already. So what we're going to talk about today is a new module. I'm going to keep this one up just because what we're going to talk about today has some relationship to what we have seen already. It's just a little bit of an extension to that. So we are moving on to injection, surjection, and bijection. And here we go. All right, so injection is summarized by f being a function to begin with. In other words, injection does not apply to f if f is not even a function. So the first thing we need to do is to make sure that f is a function to begin with. Then we can check this expression here. If it is true, then we say the function f is also injective. An injective function is called an injection. So we look at this expression here and go like, okay, that looks familiar, but not exactly the same as what we had before. So we want to compare these two, okay, just to see how they're different. So let me do the trick again. So I'm going to do a screenshot. Oops, okay. That did not work as I anticipated because I control print screen. There we go. Nope. Shift print screen. There we go. All right, so this is the first one. We are familiar with this one already. And I will paste it here. And then we go back to the other one. Shift print screen. And copy and paste. Give me a second here because once I paste, I will show you the other screen so you guys can see what I have pasted here. There we go. All right, so now we can take a look at the two expressions, and then we can kind of figure out how they're different. So these are the two expressions. The first one needs to be true in order for f to be a function to begin with. But it also requires that f is a subset of the Cartesian product between x and y, x being the domain, y being the codomain. The second one is assuming f is a function to begin with. If this requirement is satisfied, which means if this, if for all q in y, blah, 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 is true, then we can also say that f is not just a function, it is an injective function, or it is also called simply an injection. So what are the differences? Well, the first difference is the quantifiers are different. The first one uses for all e in x. In other words, my focus is for each element in the domain, blah, 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 needs to be true. The second one is focusing on y, which is the codomain. So the second one is basically saying for each element in the codomain, blah, 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 okay? Is that okay? So that's a main difference. It's a major difference because one focuses on the domain and the other one focuses on the codomain. All right, so once we focus on the codomain, what else is happening here? So we have, so once again, the overall structure of the expression is really similar because in the end, this one just wants to confirm blah, blah, blah equals to 1. This one wants to confirm blah, blah, blah is less than or equal to 1. So that's the other difference. One needs to be 1 and only 1. The other one says up to 1. can be 0. Okay? It cannot be negative because you cannot have a negative number of elements in a set. So it can be 0, can be 1, but it cannot be 2. Is that okay? So that's the other difference. So now we are focusing on what are we counting? Okay, how are we constructing this set here? We have already bound Q to be a particular element of Y because of the quantifier. So by the time we get to the set notation, it has P being unbound at that point. So that means P can be anything as long as PQ as a two-tuple turns out to be an element of F. In other words, it's basically saying, give me all the two tuples that end with Q. All right? But we are constructing a set out of all the two tuples of F such that PQ is an element of F. Q is already bound by how the universal quantifier is specifying. So we are just counting how many things from the domain maps to this particular Q. The number of things from the domain that can map to anything in the codomain is up to 1. That is the requirement of an injection. Any questions? Questions? All right, well, let's go ahead and take a look at a few examples, and you guys tell me whether the second criterion is true or not. All right, let me get back to Joplin. All right, so the first thing I need to do is to give you what is X, what is the domain. So the domain is going to be the same as before, so I'm just going to copy and paste here. And then I'll give you F, which is already confirmed to be a function, because otherwise it doesn't make sense to see if it is a injection or not. So I'll give you A1 and B1. So the question is that an injection? So you can focus on the right-hand side, which is the rendered equations. So is that an injection? Does it meet the requirement? It does not meet the requirement. Well, so now we need to explain why it is not meeting the requirements. So I'm going to use the bulleted list here just so that we can look at individual examples and also explain them under its own container. Okay, so why is this not meeting the requirement? So there are two elements in the codomain, 1 and 2. So we have to evaluate what if Q is 1. And then we also have to evaluate what if Q is 2. Okay, because we are saying for all, right? So for each one we have to evaluate and figure out what turns out to be the result of the expression that we wanted to evaluate. So in this case, the cardinality, okay, let me use the proper equation here. So the cardinality of the set of some element P ending with 1, because Q is 1 already, such that P1 is an element in F. And what would be the answer to this question? What would be the cardinality of this particular set here? If I count everything in F that starts with something, I don't really care what it is, but it ends with 1, what is the count? It is 2. Very good. So it is 2. But 2 is less than or equal to 1 is false. Okay? So we'll say this is less than or equal to 1 is false. Or we can just say spell out false. There we go. And I'm going to put in parentheses just so that we know how this is all organized. So that means the condition, the expression I need to be true for every element is false. Well, since this is also a universally quantified expression, if I find one element where the test is failing, that means the whole thing is failed. Because in order for a for all to be true, everything needs to be true. I have just found one to be false, so that should be sufficient already to say that F is not an injection. But let's just say that we want to evaluate the other one as well. We'll see how it turns out to be. So if Q equals to 2, I'm just getting a little lazy here and copy and paste the expression and just change the 1 to a 2, but I want you guys to tell me what the count turns out to be. In other words, what is the question mark here? In other words, I'm looking for elements that look like a 2 tuple. The first item of the 2 tuple I don't really care about, but the second one has to be a 2. So when you look at how F is defined, how many 2 tuples in F starts with something that I don't really care about, but ends with a 2? Nothing, right? 0. So in this case, the answer is going to be a 0, which means this turns out to be true. This is actually okay. But since the condition failed once, or at least once, for the elements of the codomain, because when Q equals to 1, we failed that requirement. So that means this function is not an injection. Are we okay so far? All right. So let me give you a test case that is a little bit tricky. And this one is tricky because the codomain is an empty set. Now, if the codomain is an empty set, what do you think F has to be? F has to be a subset of the Cartesian product between the domain, which is X, and the codomain, which is Y, and in this case, it is an empty set. What is the Cartesian product between something, which is a set, and the empty set? We talked about this before. Go ahead. It has to be an empty set. Very good. Okay. So F is as it is now, which is an empty set. So the question is first of all, is it a function? Is F as an empty set even a function? Well, let's try to evaluate the condition first, right? So we want to evaluate the condition. Let me copy and paste the equation first, so this way we can focus on just Joplin without having to flip-flop between the two, the browser and Joplin. Give me there, and we look back into this qualification. So we say copy to clipboard the tech commands, and then we switch back to Joplin and paste it between the dollar signs. There we go. All right, so we want to look at this expression and say, well, is this F even a function? Then you go like, well, we have a problem here, because the universal quantifier says for every element in X, you'll do blah, blah, blah. Well, I guess we can evaluate that because we have 2 elements of X, so we can go ahead and evaluate it. And the answer is pretty clear. It is not a function because the answer to the question that we need to ask is basically a 0. But I'm going to show you anyway. So we'll say when E is A, the number of elements in the set where each element is in the form of A something and that A something has to be found. Oh, it has to be A something, so that something is Q, is in F. That thing as a set, and we count the number of elements in it, that's going to be 0, which is not 1. Okay, so the other way to say this is if we really want to compare that to 1, it is false. So we already have one element failing the test, which means the for all has to be false as well. Does that make sense? So let me just kind of make it more clear here. In this case, f is not a function. All right, if it's not a function, then it doesn't make sense to see if it is also injective because, hey, injection only applies when we know something is a function to begin with. So now let's go ahead and flip this around. And I'm still obsessed with an empty set. So this time we're going to make both of them an empty set. So the domain is an empty set. The codomain is also an empty set. So now what can be F in this case? If I have the domain being empty and the codomain being empty, what is the only subset that can come out of the Cartesian product between an empty set and an empty set? The empty set itself, right? Okay, so that's the only way we can construct F, just like the case before. But this time, is it a function? It's weird because the qualification, which is what I'm going to copy and paste right now, says something about for all E in X, okay? But X itself is an empty set to begin with. So what do? It is quote unquote undefined, or is it actually not undefined? Do you guys remember the code, the C code that I used to illustrate how to evaluate for all? Nope. Okay, well, let's go ahead and take a look at that again. So we want to go back and, so this is not, well, okay, this is illustrating what is the for all quantifier, but it's not directly related to the example that we have. So we want to find out what exactly what does it mean when we say for all E in X P of E. What does that mean? Okay, what is the value of that thing? So I believe one time I specified in C code, and today we'll do it in a basically the same thing. So we say int for all, and we need several parameters in this case. We need the concept of a set, which does not exist in C or C++, but I'm going to pretend that it does. Okay, so X is a set, it is a parameter. And we also need a predicate P. So the predicate P, I actually do have a way to specify that. It's a pointer to a function. So in this case, the initialization of result is going to be true. And we want to return result when everything is said and done. And in between, I invented a for each construct, which actually is a construct in JavaScript and a few other scripting languages, but it does not exist in C or C++. So this is a pretend construct. So I say for each, oh, wait, I need to declare another variable here, which is the type of the type element. So E is of the type element. So for each E in X, do the following. So what is interesting here is for each element, I say result is result and P, whatever function P is pointing to, applied to E, which is an element. So this is as close as I can get to give you the quote-unquote algorithm corresponding to for each or for all. Are we doing okay so far? Does this look slightly familiar? Because I think I used something like this to illustrate the logic of for all. So this for each loop here is going to go through one iteration for every element in the set X here. So if X is not empty, we kind of know what it's going to do. If X has elements, let's say X, I shouldn't say XY, let's say ABC. Okay, if X has the element of ABC, then in the first iteration, if Y may be B, in the next iteration, it may be A, and in the last iteration, it will be C. In other words, we're just basically plugging in every single possible element into E and go through one iteration for each element of the set. But what if X is empty? Well, if X is empty, it is as if this for each loop is not even there, because there are no elements. We're not going through even one single iteration. So if the for each loop does not even exist, what am I returning? We're returning 1. So by default, if you're saying for each blah, blah, blah in blah, blah, and that set turns out to be empty, we're saying, yep, it's true. It's counterintuitive. It doesn't seem to make sense. Okay? The other way to look at for each or for all is we need a confirmation that something is false for the for all to be false. So that's one way to look at it. In the absence of evidence that at least one thing in this set makes that expression false, in the absence of that, we just say, yeah, sure, go ahead, fine. Is that okay? It is counterintuitive, but this is how it is defined. So getting back to here, now we want to ask this question, okay, which is represented on the other side over here. Is this true or not? Well, there's nothing in X. X is an empty set. So that means the for all, the universally quantified statement is by default true. F as an empty set is indeed a function when the domain is empty and the codomain is also empty. Which also means now we can ask that question of, is it injective? It sounds really stupid, right? We have a totally useless function. It doesn't actually do any mapping from anything to anything, but yet officially it is a function. And now we want to ask, is it even injective? Is that question stupid? The answer is yes, absolutely. But does this question ask to make sure that you guys understand the concept? The answer is yes as well, and that's why we're going to do it. All right, so we are going to say this is indeed true because the set X is empty. So now we're going to say, well, since it is a function, now we can ask, is it a injection? Is it injective? So let me go back and quote the injective function qualification, which is right here. So once again, you'll just copy the tag command to Joplin and put it inside $2. And now we can say, well, is that true or not? Well, the same thing happens, right? Because this time we're looking at, okay, let's look at everything in the codomain and blah, blah, blah. But that blah, blah, blah doesn't even make sense anymore because there's nothing in the codomain. The codomain is indeed empty. So that means the default answer, according to the code equivalence, the default answer is true. So that means the answer to this question is, yep, it is indeed injective because I cannot find evidence otherwise. Are we doing okay so far?
Because it exists, it's true.
Well, because it is true because there's nothing in Y. So when there's nothing in Y and you're using the universal quantifier, the first thing we do, in the quote-unquote logic of a universal quantifier is to say, yeah, let's assume it is true unless we can find evidence it is not. So if the set itself is empty, I cannot find any evidence. There cannot be any element to show that this expression is false. So in the absence of evidence of, yeah, at least for one element, this thing is false, then we have to say the universally quantified statement is true. So it's kind of awkward because, I think I used this example too, is every purple professor at ARC a good professor? The answer is true because we don't have any purple professors. Because you cannot show me, hey, there's that purple professor and he's not a very good professor. In the absence of evidence of something makes it false, we basically say that statement is true. All right. So are we still doing okay so far with this?
It's kind of like the phrasing of like innocent until proven guilty. So the it is injected until proven is not.
Right. And everything has to do with this initialization of the default answer to be true, and we are looking for things to turn it false, basically. So the only chance you can turn the result to be false is one of the application of predicate to one of the elements of the set is false. That would be the only chance to make the universally quantified statement false. All right. So let me go through one more example just to be sure. Okay, so this time I'll give you something that actually is injective. Oh, wait, but I need to make a conclusion first. Okay, so we have to make a conclusion that F is an injection. Even though it's useless, it is still an injection. So the next one is going to be like this. X has, oh, I know. We can do something like this. It has AB in it. And then this time Y has 1, 2, and 3. Okay, so there are 3 elements in Y, only 2 elements in X. And then we'll ask, okay, let's define F first. Okay. So F in this case is going to be A1 and then B3. All right. So first of all, is it a function? That's pretty clear. It is a function because for each element of X, which is A and B, it is mapped to one and only one thing in the codomain. We get there because A maps to 1, 1 is in the codomain. That's good. B is mapped to 3, B3 is in the codomain, and that accounts for everything in X. So we are good. F is indeed a function. All right. So we'll make a conclusion that F is a function. So the next question is, well, since it is a function, we can now ask, is it a injection? So that would be the second question that we ask is it an injection? Well, if we want to know whether it is indeed an injection or not, then we better look at everything in Y, 1, 2, and 3, and make sure that this expression is true for every single element in Y. Because that's the only way you can confirm the universally quantified statement. So now we say, okay, let's check it out. Q equals to 1 for the first case. Q equals to 2, and then we have Q equals to 3 because we need all 3 cases to be true in order for the universally quantified statement to be true. Okay, so let's take a look at this one. And we want to focus on the expression itself this time. So we want to ask, is this thing true or not? And that thing is this. All right. Well, we already know what Q is. Might as well just substitute 1 instead of Q. That makes it easier to look at. So we'll go ahead and change that. Because Q is 1 already. So we're looking at that. And what would that be? I mean, if you try to give me a set where every element in the set belongs to F to begin with, and the second item in the 2 tuple has to be a 1, what would be that set? This set here is just, it consists of one single element, which is what element of F starts with something but ends with 1? A1. That's right. So we just have A1 in that particular set. And what would be the cardinality of a set like that? It's exactly 1, and is 1 less than or equal to 1? All right, so it is true for this one. Let's look at the next one. The next one looks kind of weird, but we'll go ahead and evaluate it anyway. So for the next one, where Q is 2, we want to see if this expression is true or not. Oh, wait, hold on a second. I have to start with the original and then slowly turn it into the form that I want. So that means I have to use this again and put it back here because I want to work on this step by step. So we want to say if Q equals to 2, is this cardinality something less than or equal to 1? That's what we want to find out. And we're going to get rid of the conclusion from the previous line. So that's what we're asking. So we are constructing a set where the elements of this set that we are constructing has to consist of elements in F to begin with. And not only that, each element of this set has to end with 2. Each tuple has to end with 2. So you look back into the set F. Do we have anything here that ends with 2? Nope, nothing. All right, so that means the set that we are constructing is indeed just an empty set. But that's okay. What is the cardinality of an empty set? It's 0, okay? And an empty set has nothing in it. Is 0 less than or equal to 1? It is. All right, so that means this is also true. So the test is passing for the first element of the codomain. It's passing for the second element of the codomain. And for the third one, I'm just going to say is true too, okay? So that means for every element in the codomain, the criteria that we need to be true, this thing here, is proven to be true. So now we know that if F looks like this, it has a domain of AB and a codomain of 1, 2, 3. This F here is indeed injective. All right, so my watch just buzzed me to remind me to take roll, so I'm not going to do that right now. Which also gives you guys a little bit of breathing room. So let's go to a roll-taking activity. I'm going to reuse this one. You cannot see it yet, I'm just going to change it so that you can see it in just a little bit. Today's date is 0907. And let's see what word I chose on that particular day before. Sometimes I surprise myself. Onto. Okay, onto is fine. I'll just write it on the whiteboard. And I will give you guys a little bit of time to do this. All right, the time is 4:05 right now. Yeah, okay, I'll give you all the way until the end of this class, which is 4:20. All right, so as you guys are doing that, I'm going to switch back to the notes because I think we got your injection. So the next topic in the next 10 minutes or so is going to be surjection. Yep.
So I think I can understand mechanically what's going on, but do you think you can give like sort of a practical application of what injection means?
So injection is one of the 2 requirements for a function to be bijective. So in order for a function to be bijective, it has to be injective and surjective. So when it is both, then it's nice because bijective means you have an inverse function. There's a way to reverse.
Okay.
So that's what we are really getting to.
Okay, cool.
So injection by itself has some value, but it's not really that significant. It is bijection that we are trying to get to, because once we have a bijective function, it means an inverse function has to exist,
Okay, that's helpful.
which gives us certain nice things to do. All right, so are we good with the role-taking activity? Is it all done? Are you done with it? Okay, I'll just double check. Are you done? No? Okay, I'll answer that for you. All right. But being able to navigate in Canvas is going to be important, because by the time we get to the exams, you might need to use Canvas for that purpose. So I'm just going to be saying that. All right, so this is surjection. And then in order for a function to be surjective, this has to be true. You go like, but Tech, didn't we see something like this before? Let me scroll up here so people in the back can compare and contrast. This needs to be true in order for for a function to be injective. This needs to be true in order for a function to be surjective. So you look at these two and go like, wow, they look almost exactly the same. What is the difference? What is the only difference between this statement and this statement down here? Sorry?
Greater than or equal to.
One has less than or equal to 1 right here, and the other one has greater than or equal to 1 here. In other words, one says every element in the codomain has to be mapped to up to once. It can be 0, okay? So something in the codomain may not be mapped at all, which is fine, in order to be injective. In order for it to be surjective, it says every element in the codomain has to be mapped to at least once. Okay, one says up to once, the other one says at least once. So let's take a look at some examples. So we'll take a look at some examples. So X is AB again. And, this is another example, so I'm going to use a bullet point. And this time Y is. So this time I have to be careful. Okay, so Y is going to be 1, 2. And then I define F. Okay, so I'm going to define F. I'll give you an F that is for sure a function to begin with. So we have A1 and B2. There we go. So first of all, it is a function, but the question is it surjective? Oh, you guys can you see it? Yep, you can, right there. So is this function surjective? In other words, if I look at the codomain, which is Y, can I claim that every element in the codomain is mapped to at least once? Okay, is 1 mapped to? Yep, it's mapped from A. Is 2 mapped to? Yep, it is mapped from B. Well, that's good enough for me. It's exactly once, but I just need it to be at least once. So that means this function is also, and it is surjective. There we go. All right, so let's take a look at another example. And the other example is going to be A1, B1. In this case, probably not surjective, but the question is, why is it not surjective? Okay, so let me scroll up so I can point to it. Scroll, there we go. So the question is, why is the second example, it is still a function, but why is it not surjective? So in order to understand why this is not surjective, we have to subject each element of the codomain to the test. So we first look at 1, and then we ask, is there at least one thing in the domain that maps to 1? The answer is, yeah, in fact, there are 2. Well, is it okay to be more than 1? Yeah, because the qualification is at least 1, right? 2 is at least 1 because 2 is greater than or equal to 1. So that is not a problem. Then we move on to another element in the codomain, which is 2, and then we ask the same question. Is there at least one thing in the domain that maps to 2? This time the answer is no, because A maps to 1, B maps to 1 too. 2 in the codomain is not mapped to at all. So that's why this function is not surjective. It is still a function, but it's not surjective anymore. Are we okay so far? All right. And I think we can finish this entire module today because surjection is just, one is specifying at least 1 because of less than or equal to 1. The other one is saying one is saying up to 1. Let me correct myself. Injection is up to 1. Surjection is at least 1. So what about bijection? Bijection is the conjunction between being injective and surjective. So now we're combining this particular statement with this statement here. So if you look at the left-hand side of the comparison, it is the same, okay? These two are the same. One wants it to be less than or equal to 1. The other one wants it to be greater than or equal to 1. So when we have a conjunction of those two, what do we get? It has to equal to 1. And someone's going to say, but isn't that the same thing as what makes a function a function? No, not quite. Because in order to make a function, in order to check whether a set is a function or not, we are saying for each element in the domain. This is still saying for each element of the codomain. So it is still in the quote-unquote wrong direction, so to speak. But if you can make sure that this requirement is met for every element in the codomain, then the function is said to be bijective. It is both injective and surjective. Are we good so far? Do you guys remember what I said? The word injection or the word surjection is only here because we want to get to bijection. It's because when we have bijection, if a function is a bijection, excuse me, then there's an inverse function. Does that make sense to you? If everything in the domain, if every element in the domain is mapped to a unique element in the codomain, and everything in the codomain is used up, is mapped to, then we can reverse the operation and say, hey, the reverse is also going to be a function. It's called an inverse function. So why do we like inverse functions? Okay, for example, we'll think about actual applications. Md5 hash, okay, which is a function. How many people know or at least understand the basic idea behind a hash function? Okay, so basically a hash function takes a text file, a binary file, some really gigantic file, and then it just turns it into a limited number of bits. Okay, that's one way to describe it. Just by the very nature of that function, is it bijective? In other words, given an unlimited amount of processing power, can I start with the MD5 digest of a file and reverse the whole process and reconstitute the file itself? The answer is no. The second question, which is related to the first one, is are there multiple strings that can map to the same Md5 hash? The answer is yes, okay? There is such a thing, which is the weakness of any scheme like that, okay? So when you store a password using the Md5 so that you're not storing the actual password as a string in the database, so the way it works is whatever the user inputs, you take the input, the actual password, you run the Md5 algorithm, you get the digest, and then you compare the digest of the Md5 hash of whatever is input to the Md5 hash that is actually stored in the database. That's the basic strategy of checking a password. So the question is, what if the database is leaked? In other words, you let a hacker know about the MD5 hash of the accounts in a particular system. So we still don't have a way to reverse the process, right? Because given the MD5 hash, I cannot say, oh, I have a reliable process to turn the MD5 hash back into the password string itself. That is not possible. But somebody can run, all the possible strings and say, okay, so we are just going to brute force this, and we'll just basically run, all kinds of strings until we generate a table of MD5 hashes. That is also called the rainbow table. So for those of you who are interested, you can look it up. It's called rainbow table. So a rainbow table is basically a gigantic table that says, well, given this particular MD5 hash, we know at least this string is going to match the MD5 hash over here. Now, so if somebody broke into a computer system, stole all the MD5 hash of all the accounts, can that person reverse the actual password? The answer is no. But can that person look up the rainbow table and find out, oh, okay, for this MD5 hash, this string, which is kind of probably some gibberish, is going to match the MD5 hash. So that is possible. So MD5 is not a particularly reliable hash function because of the bit width that it produces. So let me just look it up. MD5 width, bit size. It's only 128 bits. So how many unique MD5 hashes can we possibly have? You can just give me the equation. 2 to the power of 128. Sounds like a huge number, right? It's not. Because the MD5 hash table exists. So for every single possible MD5 hash value, someone has already figured out what string will map to that particular MD5 hash value. So if a hacker hacked into a system and stole all the MD5 hash of the accounts, that hacker can now sign into any one of those accounts. Yep.
I'm just asking, MD5 is not even used for passwords anymore, right? I was under the impression that it was only used for checksums or file download.
Right. So instead of using MD5 now, they're moving on to, I think, SHA, SHA, SHA-2 indeed. And I think I'm not sure whether 255 bits is the longest one. I think it's the widest one. So now you have 2 to the power of 256 possible entries, and that is still considered to be a lot by today's standard. But you can also see how the standard changes. I know we're running out of time because in the good old days, when your parents first got into Wi-Fi routers, what was the standard of Wi-Fi encryption? It was called WEP, Web, Wire Equivalence Protocol. And can you guys guess what is the length of the encryption key? 128 bits. And it sounded like it was sufficient back then. It's no longer sufficient. So these days, if somebody was still using WEP, 128 bits, the trick is to look at all the traffic and rule out possibilities. So you basically look at all the possible encryption keys, 2 to the power of 128 of those things, and then you just rule out the ones that cannot possibly be the actual encryption key. Now, in order to break the encryption, it depends on the amount of traffic. If somebody does not use the internet a lot or use the router a lot, then there's not enough traffic to quickly rule out all the impossible ones. But these days, we all watch Netflix, we all stream and stuff like that. So the idea is it can be done within a week. If somebody just park a car next to one of those Wi-Fi routers using WEP, they can crack the encryption key in at the most a week. And I think with all the traffic these days, because we watch YouTube and just a constant stream of packets, It can probably be done in a day. Yep. So there are practical applications of what we are learning, because we can tell whether something is hackable, and if so, how hackable it is. So we want something that's reversible, okay? And then next time, I want you guys to kind of read ahead of me. So let me show you what I want you guys to be reading at this point. So we are done with functions, okay? We are done with functions. I am going to release the function assignment. So that would be your assignment over the weekend. This is the one that I'm going to release. Actually, there are two. So I'm going to release one at a time. This is going to be the one that I will release. So the next time, we're going to talk about Aleph No. So Aleph No is an interesting module. And I am going to start with a question so that I can get you guys started. So I want to compare the set of all integers with the set of all natural numbers. Okay? Each set has an infinite number of elements, right? Because there's an infinite number of natural numbers. There's also an infinite number of integers. So the first question is this true? Is the set of natural numbers a subset of the set of all integers? So that's the first question. The second question is asking about the cardinality. So if I were to compare the cardinality of the set of all integers with the cardinality of the set of all natural numbers, what would that be? Would that be equal to? Would it be less than? And how can we even compare? Because this is infinity, this is also infinity. How do we compare that? Well, as it turns out, once we get to Aleph No, there'll be an interesting question. Because as it turns out, they have the same cardinality. We can actually say that they have the same cardinality, and yet one is a subset, a proper subset of the other one. So it's not even that, it is that. Because guess what? -3 is not a natural number. Neither is -2. So we have some really weird situation where we can say, yeah, the set of all integers contain everything in natural number, but not the other way around. And yet we can now claim that they have the same cardinality. It's like, what? That doesn't make sense, okay? So that's what we'll be dealing with next Monday. And there are some really kind of interesting stuff too within this module. So read ahead of me, because the concept can be a little bit abstract, okay? So read ahead of me, and then I'll explain all of that stuff next Monday. I'll give you the assignment in just a little bit. I will make an announcement. All right, so you guys have a nice weekend. It just feels weird to say that on a Wednesday, but it is what it is.
Thank you, Professor.
Yep, thank you.